You are recording. We're going to start. Thank you for signing up today and welcome to everybody. This is a presentation by the Norway California Business Association, NCBA. And today with me, I have two members of the board, Tom Nordheim, who's also the speaker, and Francis Mohajirin. I'm the president. Norway, yeah, and let me just ask everybody who signed up, can you go into the chat, the little bubble on your menu, and just put in where you're coming from? That's always fun to see how, which states people are coming from, which and so forth. So please do that, and we get back to and read that up. Somebody's already doing that. Fantastic. Thank you. Norway California Business Association, we're developing and initiating collaboration between Norway and organizations in Norway and organizations in the US, especially California. We have a very close relationship with JPL. Both Tom and I work there, and we've been helping them initiating contacts with organizations in Norway, both JPL and also NASA headquarters. And we also work on developing opportunities for interns from Norway at JPL and other organizations. And we try to focus on areas where Norway and California have a lot of things in common. So we had a big conference on sustainability, which is a big thing in California as well as in Norway. And ocean is also a big thing. So we had a big conference a few years ago, actually over 2 years, focusing on what we call the conference CESNI, and we were focusing in on sustainability approaches in the shipping industry, and again with participants from Norway and California, but also from a number of other countries. So going further on ocean, we are also focusing in on collaboration opportunities for Ocean Worlds, one of the new areas of focus for JPL and NASA. And we have, okay, somebody might want to mute themselves there. We're developing specific relations now with SINTEF and TNU, a number of other organizations, Polar Institute, the Space Agency, and we just had a letter of intent being signed by JPL, a SINTEF proposal to the Research Council of Norway, and that is happening right now, and that's an example of what collaborations we're initiating. And since we're seeing this closer collaboration, we set up this set of webinars. We talked about the science and the more, what is Europa, what is Enceladus, these ocean moons. We talked about that before. We talked about the EELS project. And today we're going to talk about the BRUIE and Tom Nordheim's work. We're going to get into that in a second. And next month, we're going to talk about, I must say that also now. We can talk about another robot that actually will drill, water jet, etc. itself through the ice on potentially Europa as we go forward. But today, focus is on Tom Nordheim, and let me go to the next page here. The title of the talk today is Exploring Icy Ocean Worlds in the Outer Solar System. And you see from Nordheim, he just doesn't sit in his office and do PowerPoint presentations. He would actually go out in the field and do work. And he's going to talk more about that. But let me tell you a little bit about his background. Tom Nordheim is a research scientist in the Astrobiology and Ocean Worlds research group at NASA Jet Propulsion Laboratory, part of Caltech. We also, for short, say JPL. His work is focused on the science and exploration of icy worlds in the outer solar system. He is a member of the science teams of the Cassini mission to Saturn and the Europa Clipper mission to Jupiter. He is also a member of the project science team for Europa Lander, a mission concept for robotic lander that would search for signs of life on Jupiter's ocean moon, Europa, hence Europa Lander. When not doing science, Tom works on robots that help us explore extreme environments on Earth and that one day will allow us to explore exotic locations in our solar system. He holds a bachelor's in space science and robotics from the University of Wales, a master's in space studies from the International Space University, and a PhD in space physics from University College of London. Okay, before we take you and give you the podium, Tom, we're going to see where people are from here. Let's see, I got 8 signed up. We got San Diego, we got Denver, Colorado, we got Honolulu, Hawaii, we got Princeton, New Jersey, and we got San Francisco, and we have even, oh, there is more here. And let's see, Francis, of course, is from Los Angeles, Beach Cities, and let's see, Cynthia, California, and California. Okay, so yeah, good spread. Thank you for doing that. Appreciate that. And so let's see, do post that one. There we go. All right. Tom, well, then I'll leave the podium to you, and we're looking for a great talk. And thank you for joining us and being part of this.
Great, thank you, Knut. If you pass the ball to me there now, I can.
That is exactly what we're going to do. Let's see. Here we go. Here.
And just to remind everyone, if you can, please mute your microphone, just so we avoid the echo.
Yes, there we go. There we go. And you're ready to go.
All right.
I'm going to switch up the camera so we can focus in on you. And
sir.
you should be ready to go.
All right. 1 second here.
Oh yeah, when you're doing that, I forgot to say, if you have any questions, please put them in the chat box, and we'll call up on you after the talk, and you can ask your question. That's that way we'd like to have you involved. So if you don't mind, please do that. Okay, Tom.
Right, perfect. Thank you, Knut.
Sure.
So as mentioned, I'm a researcher at the JPL. I focus on the search for life in what we call ocean worlds in the outer solar system, and I'll talk a little bit about what those are, and also on building robots that we will one day hopefully use to explore these kind of environments. And of course, I should mention that I'm part of a big team that's working on this, and of course, it's not just me, but it's a large effort that has taken many tens of people over at least 10 years. So I just want to recognize that straight off the bat. Now, let me just see if I can minimize this. Oh, there we go. So when we say icy worlds, what we're generally talking about is the moons, the satellites of the 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, as well as a few other objects further out, such as Pluto and its moon Charon. Now, most of these moons, basically the rock on these moons, a large part of the composition, if you were to stand on the surface, is actually made of water ice. So we call them icy worlds. And here are just some examples. And these icy moons, some of them, and you'll see these check marks here now, we know to have subsurface oceans of liquid water beneath these icy surfaces. And so those include moons of Saturn and Jupiter, things like Europa and Enceladus. But I should say that we haven't really looked for these ocean worlds properly or very exhaustively. So it's likely that this picture, maybe 50 years from now, will have a lot more green check marks, and we will have found a lot more of these alien oceans, these ocean worlds beyond the Earth. And so the most famous ocean world is perhaps Jupiter's moon Europa, which when you look at these images, apologize if this is a little bit grainy here. These are images from NASA's Galileo spacecraft. And you immediately see that this is a very interesting object. It's this surface filled with these cracks. The surface is very young, so that means that there are not a lot of craters. And that gives us an indication that something is acting on the surface, refreshing the surface and modifying it. Also very interesting is when you look at high resolution images of this moon. So this is some of the highest resolution images we have of Europa. You again see these cracks, the surface that's just riddled with these cracks. But you also see this reddish brown material that seems to be associated with these cracks. We think what that is actually ocean water perhaps coming up from the ocean below, making it through perhaps tens of miles of ice, and then being placed onto the surface. So this brownish red material may be an indication of basically ocean water from below, and it could even contain possibly signs of life if there is life within this ocean beneath the surface. Now, the other famous, I would say, ocean world is Saturn's moon, Enceladus. And this is actually a pretty tiny moon. It's about the size of England. And before the Cassini spacecraft arrived in about 2004, really the expectation was that such a tiny moon, it would have cooled down from when it formed, it would be completely dead. But Cassini discovered something drastically different than that. So when it arrived, it discovered these massive jets emanating from the south pole of the moon. So we're really looking at this kind of flipped on its head right now. But of course, there's no up or down in space. But it discovered these massive jets emanating out from the south pole. And these jets appear to be fed by an ocean, a global ocean beneath the ice. And what's really exciting about this is that because we have these jets coming into space, we can actually take the Cassini spacecraft. Even though it wasn't really built for this purpose, we could take that spacecraft and fly through these plumes or these jets. We could actually sample directly what was the composition of the ocean and this material coming out. And so we found, of course, a lot of water, but we also found things like CO2, methane, ammonia, and hydrogen gas. Even more interestingly, we also found both simple and complex organics, and organics up to very large organics, which appear to be a major constituent of this ocean. So in terms of the search for life, this is really exciting. And this is kind of the picture we're left with of this particular ocean world, Enceladus, with this kind of post-Cassini understanding. So we think that there is a global ocean, which is in contact with the rocky seafloor. At this rocky seafloor, we think there were hydrothermal vents. So that's similar to the black and white smokers we find at the bottom of the Earth's ocean. And that's also very exciting because one of the prominent theories for how life formed on Earth is actually around these hydrothermal vents. It's also interesting from the point of view that these hydrothermal vents induce a lot of chemistry into that ocean that's beneficial to life. We also think they're beneath this ice crust on the surface, and I should say there's no atmosphere, so there's just a surface made of water ice and it's exposed directly to space. And then you have these plumes coming out fed from the ocean. Now, a relatively recent finding from the Cassini data is also that we think there is a kind of a layer enriched in organic material right underneath this ice crust, right at the top of that ocean. And so that's really showing us that, you know, if we want to go look for life on these ocean worlds, you know, one of the best places we could go look for this life is actually right underneath that ice shell, right at the top of the ocean. And there's some interesting analogies to life on the Earth. So this is a cross section of sea ice in Antarctica, and you can actually see this brownish red material growing here, and that is actually sea algae that lives underneath the ice and lives off of the reduced but still present sunlight that makes it through the ice, and also feeds off of nutrients there. This is an example from the Arctic Ocean, and this again shows a sea algae that lives underneath that ice shell. So we have some really interesting examples of on the Earth, perhaps a similar, in some respects, type of life to what we might expect to find on these ocean worlds, if there is life in these objects. Now, so I already kind of stated that if we want to go look for life on these objects, the bottom of that ice shell is really a perfect place to go look for it. And so, you know, we were kind of brainstorming and we were thinking, well, if you want to go look for life underneath that ice shell, what kind of robot would you want to do that sort of task? And so, of course, at JPL, we're famous for making Mars rovers, and there actually will be a Mars rover, hopefully landing successfully on Mars on, I believe, next Thursday. But obviously, this is not Mars. So we had the idea, what if you took a rover and drove it upside down. And so that's led to this concept that we call BRUIE. And first, this was really a simple kind of 3D printed little robot where we had the idea that it would float up and have these spikes on the wheels that would give it traction on the ice. So it would drive upside down underneath that ice. Of course, this is a relatively crude initial concept, and it further was developed into what we call the Buoyant Rover for under ice exploration, called BRUIE. And here are 2 early prototypes of that. And of course, once we had this rover, we wanted to go somewhere where we could test this sort of technology. And so the choice fell on Barrow, Alaska. And you see Barrow indicated up here. It's actually the northernmost point of the United States. There are no roads that take you south. The town is completely isolated. There are a few miles of ice roads, but that's it. It's an extreme environment in many ways, but actually life is still thriving there. And what's also really fascinating, and you can see a picture, a satellite image of Barrow here, you have access to both sea ice. The sea freezes over every year, and you can see it here. This is all ice facing right onto the Arctic Ocean there. But we also have these lakes, and this area is riddled with these thousands of lakes that also freeze over in the winter. Another important aspect of what we're doing, we're preparing for exploring ocean worlds, maybe decades into the future. But today we can also use these sort of robots to learn about the effects of climate change on these Arctic regions, where the climate change effects are much more rapid and much more devastating than what they are closer to the equator. So I should mention that that's also a big part of what we're doing. We're also conducting climate science. We're also trying to understand how those environments respond to the increasing temperature. So really a huge advantage of going there is that we can actually take a commercial flight. We can take an Alaska Airlines flight up there. And here you see a sneak picture out the airplane window with the baggage handlers unloading our robot. And then we take a snow machine out into either the frozen sea ice or the frozen lakes. And so this is a rugged environment, but it's also a relatively accessible environment. And that's really useful considering that we have to take hundreds of kilos of equipment up there. And we have to also sled it out to the field site. So this is an example of what we call Nasaville USA. This is a camp on the top of a frozen lake, about 30 miles outside of town. And things can get pretty rugged out there in the wind, despite the fact that it's relatively civilized. And so while this is convenient, I shouldn't downplay the fact that it's still definitely a extreme environment where we have to take certain precautions. And in this case, Nasaville was being exposed to a pretty severe snowstorm. And we had to load down the tents with some snow and take some precautions there. So this is showing an early prototype of the rover. As you can see, it has these spikes on the wheels, so it will then float up underneath the ice and use these spikes to get traction. You also see that there's this tether for communication. So it unspools this tether that's then connected to a laptop on the surface that we use to control it. Here's an example of the rover being deployed into a freshly dug hole. And this is an example of, from the point of view of the rover, what it looks like, one of these deployments. And I should say, actually, what you can see there, you see those bubbles seeping up, and you see these bubbles in the ice. That's actually methane that's frozen into the soil. That actually is thawing up and being released in these lakes. And from the perspective of climate change, that's actually a really important thing to study that hasn't been very well quantified yet. Of course, due to the changing climate, more and more of this methane is being released from these lakes. And methane in itself is, of course, also a potent climate gas in itself. So you have a bit of a feedback effect there. And so this is very important to study, in situ, in the environment, to see how much of this gas is being released and at what times and in what way. And I'll move on to the next slide here. Now, that concept worked relatively well, but it had some drawbacks. And here's an example of the rover getting completely tangled up into the tether, and the tether cable actually getting sliced by these very sharp wheels. So clearly, there were some improvements that needed to be made here. Another aspect of this particular iteration of the rover was that it didn't really have any localization. So we actually had to go brush off the snow from the ice and look at it visually to see where it was going. Not very practical. This is the most recent version of BRUIE. You can see it looks a little bit different. One of the big differences is that it now has redesigned wheels. So instead of just those sharp spikes, it now has the spikes for hard ice. It also has these kind of paddles for softer, more slushy ice. And that gives us a lot more flexibility in terms of where we can go. We also have these two independently rotatable pods. And that's really useful because it can let us conduct science investigations on two different targets at once. And it also lets us have the ability of, for example, directing one camera downward and using the other camera facing forward to look at where we're going. We have these modular instrument bays where we can fit a number of different types of environmental sensors to look at things like pH, oxygen content, methane content, salinity, things like that. And we also have these very powerful lights, which of course is useful when we go deploy this in the polar night up there. It's completely pitch black. Even when there's daylight, we're underneath the ice. And so having this powerful illumination is important. And this is also something that would be very important, obviously, on in the ocean world, such as Enceladus or Europa, where you have maybe tens of kilometers of ice and very little, if any at all, sunlight could make it through that. We also have an onboard localization and data processing unit here. And so what we do is we deploy sonar buoys beneath the ice. And that allows us to both communicate with BRUIE over relatively large distances. It also allows us and the rover itself to localize itself. And so we can figure out where it is, and it can figure out where it is without us having to go look for it on top of the ice. And we've already seen that. This is an example of a what we call a Bronicle. So here we've taken the rover and driven up to what these are basically, as the sea ice freezes, the salt in the salt water gets excluded and it gets drained into these drainage channels called Bronicles. And this is a great example of something we think would exist on Europa and maybe Enceladus. And it shows how we were able to kind of maneuver up to this relatively fragile feature and investigate it with the rover. And this is something that would be very difficult to do if we were to drill through the ice, where we'd be disturbing this environment, or if we had a submarine type of vehicle. So this under ice rover is really the perfect thing for investigating these things that are at the bottom of that ice. Here's another example. Here we actually use another little follow submarine to test some procedures. So what we've done here is that we have these science instruments that are located in the tail of BRUIE, and we've actually rotated around and swung that tail carefully up next to this Bronicle feature to investigate it. And again, this is actually pretty fragile kind of feature. And so having this wheeled rover with these rotatable pods lets us have a lot of fine control, and we can do this very carefully without disturbing the environment. I should also say that these wheels that we have, they leave very minimal impact on the algae growing underneath the ice. Whereas if you drill through the ice with something like an auger or ice fishing kind of drill, you're really just ripping up that whole environment. Here is BRUIE from a recent deployment at Casey Station, which is a Australian Antarctic division based down there, where BRUIE was deployed along with the happy penguin here you can see. Here you can see a picture underneath that ice in Antarctica, and this is really fascinating. I mean, it's a place that is considered to be pretty cold and pretty dead, but actually once you get underneath that ice, you see this brownish material here. This is full of sea algae that are living underneath that ice. And we also found, of course, a thriving environment of these little krill and fish living underneath here. So it's really showing how fascinating these environments are in their own right, and maybe giving us an idea of maybe the possible things we could find on an ocean world. It's a bit speculative, but still. And I'll leave you with a short video here, which was actually made for us by National Geographic, which came along on one of the expeditions.
The rover that our team has developed is an early precursor of something that we may someday fly to Europa. The Buoyant Rover for under ice exploration is designed to float on the underside of the ice and rove as if the underside of the ice is the ground. These ecosystems up in Alaska, these lakes that freeze over every year and freeze down, they're just one example of life in an extreme environment that can help guide us in assessing whether or not a world like Europa could harbor life. We cut a hole in the ice, put the rover underneath the ice, and then left it out there to rove around. And we went back to the nice warm Quonset hut, and our team was even able to hand over control to engineers down in JPL. And so we think this truly was the first time ever that an underwater, under ice, untethered vehicle has been operated through satellite link. Our work has this wonderful marriage of advancing our understanding of what's happening on our own planet while simultaneously feeding forward into our exploration of potentially habitable worlds beyond Earth.
And so we're left with this kind of possible roadmap for ocean worlds exploration. And here it's showing what we would like to call Europa Vision 2050. So this is Jupiter. This is Jupiter's moon Europa, which we think is one of these ocean worlds. Very similar to Enceladus in the way we think there's a rocky seafloor with hydrothermal vents, an ice shell, and this material maybe venting into space. And so currently, the next NASA flagship mission after the current Mars rover that will land next week is Europa Clipper. So that's going to fly by Europa many times and study its ice shell with spectrometers, cameras, radar sensors to really characterize that ice shell. And then the next step could be something like the Europa Lander, which is a mission concept that JPL has been studying under direction by NASA. And this would be something that would actually go land on the surface, maybe look at some of this material, this reddish brown material coming up from the ocean, and looking for signs of life within that. And then, the next steps would be maybe something that could move along the surface, maybe some sort of spider robot. And then we'd want to get through that ice shell and into that ocean. And one possible way of doing that is through a radioactive drill. And Knut and I have both been involved in a project that was unfortunately not successful, but it was an internal project at JPL called PRIME, which was looking at drilling through this ice shell. But then once you get through that ice shell, really the perfect vehicle to look for life and explore the underside of that ice would be something like the BRUIE vehicle that we're developing. Ultimately, maybe far in the future, maybe 2050, maybe later, we'd be looking at the deep sea submarines that could maybe take us all the way down to the seafloor and look at those hydrothermal vents. But for now, we're preparing the technology that we think will enable us to do this sort of science and go explore these ocean worlds and look for possible life beyond Earth in these environments. And so with that, I'd like to leave you with this picture from our most recent field campaign, where we've just happily deployed the rover. And I'll take any questions.
Great, thank you. Hang on. Yeah, where are we going to do this? I'm sorry. We have a question from Cynthia first, so let's start with that. Cynthia Dorado from California. Can you unmute and ask your question?
Yeah, no, I was just wondering if all the scientists are, outdoors people and just ready to deal with that environment, or did you train ahead of time, or like my actual question was, how many days are you actually testing? Or
well, it's a bit of a mix. Some of the team are very outdoorsy, some are not. The advantage we have of going to Barrow is that we have both of these really interesting environments, the frozen sea ice and the frozen lakes, within a few tens of miles of town. So we can stay, there's a former naval base there, now research center where we stay. And we generally don't have to overnight out on the ice. We can deploy the rover, leave it in for maybe a week and go check on it every day. So that's a pretty nice feature of being there. We do have to have a bit of training. And anything from snow machine driving to what to do when a polar bear attacks, and we actually had a very close encounter with a polar bear and 2 teenage cubs last time we went up there, which was pretty exciting. Yeah, it's important. There's definitely some important training that we have to go through for this, but going to Barrow really makes it a lot nicer because we can just fly up there. We can stay in the accommodations up on the base there, and just go out on the ice with our snow machines.
and then you mentioned you put buoys at different areas, so you wouldn't have to like uncover the thing. So like, what would be the icy world equivalent of that? Like, what would you do?
Yeah, that's a really great question actually, and it's one of the most challenging questions of how we would do this, because on somewhere like Europa, which has an ice shell of tens of miles, we'd have to find a way to communicate through that ice. And one of the concepts we've been looking at is if you were to have a drilling robot, it would deploy these little communication pucks at regular intervals within the ice. So you would have kind of a chain that you'd be able to communicate up to the surface. And there are different ways. One is using acoustic signals, which is something we use right now. You could actually also use radio signals, and you could also use a thin fiber cable that you actually deploy. And the concept that Knut and I have been working on actually would use all 3 of these to have like some redundancy in case one broke down. But that's a really great question. And right now we're drilling through not very thick ice, a few meters maybe. But ultimately we're talking about miles, and then it starts to get really challenging. So yeah, great question.
Okay, there was another question, so please come back again and unmute yourself. If you got a camera, feel free to turn that on too. Didn't I hear another question from another person? No? Okay, well, let me ask you a question then, Tom.
Sure.
You mentioned Barrow, Alaska. I know, for example, eels are planning to go and test at Svalbard, another location that's really easy to get to. Can you share some thoughts about that location too? Svalbard, by the way, is a Norwegian territory up in the north. And of course, Tom is from Norway, and so am I. So for him to deal with these Arctic climates is not that hard.
Yeah, it's definitely a bit of a, what do you call it, a home field advantage.
Yeah, exactly.
Yeah, we would love to go to Svalbard, and Svalbard has many of the same things that Barrow has, access to. Maybe even more excitingly, Svalbard has some glaciers where you could actually potentially drill through quite a thick ice layer. Because when we get to the point where we're really testing these ice drills in the future, something like Svalbard or Greenland or Antarctica would be perfect. And so, yeah, we'd love to go to Svalbard.
Yeah. Yeah, we're actually planning to, the EELS project, as I said, is planning to go to Svalbard for testing. And we found, or there are caves there in the ice and in the rocks that this eel, which actually looks like a snake or an eel, can climb through. And there are also places where, as Tom said, there are thicker ice. It's easy to get to ice glaciers that are about 10 kilometers long, so we can test communication, like Tom talked about earlier, where we would place a communication system on one end of the 10 kilometers and one on the other. So suddenly you start getting a little bit of an understanding about what happens when you communicate wireless over long distances, again, using acoustic. And we look at different frequencies for different types of ice, but that's a different story. That gets to be too much detail going into. But I'm seeing many questions here. So Frank C, do you want to ask your question? And if you got a camera, please feel free to join us.
Yes, I can ask a question. Let me see if I can. Hi. Yeah, I was just wondering, so since you just have two wheels with a body, it seems like the body would just want to rotate and the wheels wouldn't go anywhere. So it looks like there was like a white rod sticking out. Is that some kind of ballast or something?
That's a good question. That actually is serves a dual purpose of being kind of a stick that prevents us from rolling around, but also by touching onto the ice, it's also our instrument payload. So we put instruments at the end of that tail, and that gives naturally access to right that underside of the ice that we want to study.
Oh, I see. And then the other thing was, I mean, you want it to float up to the bottom of the ice, but you need to have it submerge down a certain amount before it floats back up. So do you pump water into it and then pump it out, or?
We actually, the way we've been doing it so far is a bit more low tech. We make it positively buoyant, so it will naturally float up, and then we push it down with a stick underneath. And it also has the advantage of if something happens to it, it will have a tendency to come back up. But that's definitely the sort of detailed logistics we'd have to figure out before we would send something like this to Europa. But for now, we have a special rover pushing stick that we've made.
I got it. Okay.
Now this is absolutely a prototype, but it's being gradually developed very excitingly and gradually and carefully. So yeah, but it's a good question.
Yeah, absolutely.
Thank you.
Yeah, let's see. And then we have Brian Harris. Do you want to join with your question? So first unmute maybe, and if you got a camera, feel free to join, turn that on too.
Well, I can answer the question if.
Yeah, maybe just do that.
Yeah. So Brian asked, how would such a rover be kept powered underneath the ice layers of these worlds? So that's a good question. I think right now the only viable alternative for kind of long duration mission would be a radioactive power source. And so we have these types of, we call them RTGs. They're kind of like a radioactive battery that uses the waste heat from a decaying piece of plutonium and converts that into electricity. And so we of course haven't gone to the step of creating this robot for Europa yet. We're still, like Knut said, at the prototyping stage, but we'd probably most likely have to have some sort of radioactive power source. Sunlight is obviously no option underneath the ice, and batteries will only really take you so far, whereas one of these radioactive power sources could keep you going for years. So that's a good question.
Cynthia, I just wanted to make a comment back to you here. It's so good to see your daughter there. Is your daughter, right? It's a little hard to see. Yeah, it is. We're also, for example, at JPL, we have internships for, younger students coming to work with us. And so there are definitely opportunities if you and your daughter are interested in being part of this. There is a STEM education. Oh, that's another picture.
I'm not a younger student. I'm a high school teacher. So like the internships I believe you guys have are for college people.
Yeah, but
they're actually available for high school students.
With your daughter there, or was that another
They're
one?
available for high school students too?
Yeah, last time I checked.
Yeah, we definitely have for students.
Then I definitely have some high school students right here on the call. So we'll see.
Perfect.
Okay. Yeah, no, I mean, we encourage contacts with us to intern and be involved. And yes, we've had some absolutely absurdly bright students, even at the high school level, coming to work with us. I had one that.
And generally, JPL scientists are also pretty happy to talk to high school classes and school kids. And it's actually an important part I didn't really mention in my talk, but every time we go up there, we make sure we spend at least one full day on outreach, going into the schools up there on the north slope of Alaska. And so that's definitely a big focus of what we do. And considering the time frame of these investigations, I showed Europa 2050. We really are absolutely reliant on inspiring the younger folks to go and do this exploration once we get there.
Yeah, because first I will retire, and then Tom will retire, and then we need to depend on the younger generation. So yeah, it's actually very important. So encourage your students to be part of this. Absolutely, that's one of the reasons we're doing this too, this outreach, because we consider this as outreach. So yeah, I just want to mention that. I think it's actually not just want to mention it. It's something we're very eager to make sure that we cover always.
Yep.
Okay, Curran, you had a question. Do you want to get on the camera and ask your question?
Yeah, sure. Why not?
Yeah. Hey, good to see you guys.
Hey, Tom. Thanks for the presentation. So my question is, what other light apertures do you have on the rover? So you have the normal aperture for, illuminating the way, but do you have like any IR? Do you have any ultraviolet to see what else is there as well? Maybe even night vision, which could be IR.
Yeah, so the main way that we see underneath the ice, so nominally it's completely pitch black. And so we need to really provide our own illumination source. So right now we have some regular, white light, very powerful white light LEDs. But there are different things we're obviously looking into for ocean world exploration. For example, the Mars 2020 rover that's landing on Mars next week. It has some interesting instruments geared at looking for organics and signs of life on Mars. One of them is an UV fluorescence instrument.
Yeah.
And some version of that I could easily imagine being on a future under ice rover on Europa or Enceladus. Similarly, we can study life both in the ultraviolet and in the infrared. And depending on what wavelength you look at, different signatures of life or biosignatures will have specific fingerprints in different wavelength regions. And so we can usually learn a lot about things by looking at them at these different wavelengths. Yeah, great question. And I think I would definitely want to take some sort of UV fluorescence type instrument where you're shining a UV light on the target and looking at the stimulated light that happens when you do that.
Let me add in there, because I worked on something similar for ocean. It was called Lohi Probe. We developed that as part of my team at JPL, and well, that's a few years ago. And that went down to the same thermal vents or black geysers that Tom talked about on the ocean outside Hawaii. And Lohi is, of course, one of the gods of the Hawaiian god, hierarchy, so to speak. And we used UV fluorescence there to look for life. So this is actually a very interesting technology, and we got a lot of experience doing that. So yeah, you should definitely put that on top.
Yeah, and I should say there is a this UV fluorescence instrument on the rover is called Sherlock.
Yeah.
And there is actually a colleague at JPL, Mike Alaska, who's made a version of Sherlock to be called Watson. That's being used to, they drill through the ice in Greenland, and they've been deploying this Watson instrument down the hole. And he's been showing some really interesting results, showing actually there are a lot of little life forms, bacteria, that live inside this ice that just metabolize very slowly and just live, within the ice itself. And this is really fascinating to see. You're drilling down maybe 100 meters into the ice, and there's things living in that ice. And so there are already some efforts at making those types of instruments for these ocean worlds.
Yeah, and actually that was one of the things talking about the prime. We're going to talk about that next time, by the way. Tom talked about the surface. There might be ice on or life, or at least signatures of life that we might even see on the surface if it's not been radiated to pieces. But even if it has been radiated, we might find extant life, meaning life that is dead, but we can still see the organic molecules potentially. So that's the surface. But then people have a tendency to say, well, okay, we need to go to the ocean to look for life. But following Tom's talk and Mike Alaska, you would actually also very likely see life in small pockets of water in the ice, or actually it could be also air bubbles as you go down. So there's a lot of you don't need to go to the ocean to see life. You probably will see it in the ice column, and this is what Mike Alaska has seen, and we also see that a number of other glaciers. So it's a very interesting, a lot of interesting questions here. Let's see, Mike Aquino. Thank you so much, Curran. Mike Aquino, you had a question. If you unmute yourself and maybe put your camera on, then we can talk. We can have a chat.
Oh, yes. So my question was, how would the rover keep up with the water pressure? And then how deep would the rover actually be submerged in the waters?
That's a great question, Mike. And so what we're looking into right now, we have a rover that can be deployed underneath, a few meters of ice. It's actually been designed to withstand pressure down to 800 meters depth. But as you said, one of the considerations we have is this variable pressure. And so if we want to be able to change the depth that we're at, for example, if we're underneath a large iceberg, or if we're underneath an ice shelf where the frozen land ice is going into the ocean and meeting the ocean, then we might have to operate quite deep. And so we're actually looking at that right now, ways that we could change our buoyancy. And so, for example, using ballast or inflatable bladders inside the rover to change that. So that's definitely something we'd have to consider.
Yes. I also have another question that I just thought of.
Yeah, go ahead.
Based on the differences within gravity from here on Earth and on Europa, would you have to account for those differences, since here it might be more?
Yeah, I haven't thought about that specifically too much, but it's definitely a difference. The gravity on Europa is about the same as the moon. So it's quite a bit lower. I think the most direct way that affects us is that it will affect the buoyancy calculations. So there's the counterforce of gravity dragging you down, right? So for the buoyancy, we definitely have to take that into account. It also means that it's easier to land on Europa than some larger bodies, like Mars, for example. Mars has an atmosphere, but it also has much larger gravity than Europa does.
Tom, I think I might help you a little bit there.
Sure.
I think you might be talking about pressure, and the pressure could actually squeeze and crush the rover. Is that the question, really?
Somewhat.
Yeah, okay.
Yes.
So the calculation for pressure is a linear. There's a linear correlation between pressure and gravity. So, if, for example, if you take Europa, if you go down to 40 kilometers or so, that's about 3.5 to 4 kilometers of ocean depth on Earth, because the gravity on Europa is about 10% less than Earth. And yes, you are very right, and I think we should ask you, Tom, if you're looking into that, because the pressure is going to crush you. And if you're anybody who's a free diver, or well, not so much scuba, but especially a free diver, you definitely know what pressure is. It hurts. So any cylinder or any object you put up at the high pressure, 3 to 4 kilometers on Earth, that's going to be crushed to pieces if you don't take into consideration the thickness of the material in your vessel, as we would call a pressure vessel at that point. There's also a way you can use liquid that is non-compressible to achieve the similar. But then, of course, you would have problems with electronics that's in the liquids, and not all electronics can deal with the liquids. But yeah, there are a lot of questions there. And I think the question would be very interesting for you, Tom. Have you looked at, do you need pressure vessels for your rover, and how much is that going to increase the mass that you're envisioning, or are you not there yet?
Yeah, like I said, our current rover is rated to about 800 meters. Right now, we haven't really designed something to go deeper, just from the point of view of we're at the stage where we're testing things at much more shallow depths.
Oh, sure, of course.
And that would give us a constraint that we don't really need to have right now.
Sure.
We have another project that's pretty exciting, which is called Europa Lander, and that's actually developing the sort of technology you would need to go to perhaps the bottom of the ocean on Europa. And there we actually have created these small robotic lander vehicles that are slated to be deployed in the Mariana Trench at the deepest oceans on the Earth.
Mm-hmm.
And the idea there is that we have these small, relatively cheap robotic kind of landers that can go down and hop around on the surface. And because this is so deep, we're designing these to be autonomous, so to be able to do their own autonomous navigation and science. And that actually will be a very key piece of technology for going somewhere like Europa. Not only do you have the lifetime delay between Earth and Jupiter or Saturn, but you also have the challenge of communicating through the ice. You might not be able to have regular communications. And so a really key capability that we actually need to develop is autonomy and types of artificial intelligence that can really deal with these relatively uncertain environments, and maybe even act as robot scientists. It might be too cumbersome to communicate back to the scientists on Earth like we do with the Mars rovers, but these vehicles may have to be able to find something that's scientifically interesting and plan its own science investigation of it without human intervention. So that's also a pretty interesting topic, I think. Sorry, I went off on a bit of a tangent there from gravity and pressure, but I did want to plug that project as well. That's also pretty exciting.
Of course. Yeah. But did we answer your question then?
Yeah.
Okay. But no, seriously, was there anything else you felt we didn't cover?
There might be, but well, at the moment I do not have any questions. However, if I do, I would bring them up.
Okay, fantastic.
Thank you, Mike.
Yeah, great. Yeah, we sort of get into the top of the hour too, I see here very soon. So maybe we should say that is the end of the questions. And I pulled up the, do you see the presentation? Yeah, you all see that. That we started with, and we're going to say a few words about where we're going next. Next, we're going to talk about the Prime. And it's probably going to be myself or Jean-Pierre Floreal, who is a PI. Unfortunately, that didn't win, but we have a lot of materials we can discuss. And this is not a competition between rovers or technologies. It's just we want to show you all the exciting stuff we're doing. We talked about the eels again earlier. We talked about the Brewery today. And Jean-Pierre, we're going to talk about the Prime, which again is a robot that's going to drill itself through the ice on potentially Europa. And this ice can be more than 20 miles thick. And it will do that by first, as Tom said, being autonomous. It's going to use drill, water jetting, and heating from a radioisotope type of power source to drill through. This could be taking years, and it will have to communicate up to the surface, and as Tom also mentioned, via pucks or communication pucks that will receive and send, as well as also with a combination, I should say, with fiber optics. And we're going to test, the plan is rather to test it on Svalbard as we go. And this is another very exciting technology. And if again, going to the last question about pressure, you cannot go to these depths in ice because you will also see the hyperbaric pressure in ice without being taken very seriously into consideration the pressure environments you're going to live in, because otherwise you'd be crushed. And we've seen this with cryobot type technologies before. And so that's also a very exciting discussion. So that's on March 10. And then in April, we're going to have a talk by SINTEF. I mentioned that JPL just signed a letter of intent with SINTEF for a proposal to the Research Council of Norway. And the idea for that proposal is to develop autonomous GNC, guidance, navigation, and control, and hazard avoidance using machine learning as the driving technology. And they will talk a little bit about what they're doing and how we're working together, and also other projects. I'm already discussing with them another proposal for the EELS robot. And I should also mention that all these collaborations will also include researchers as well as interns. And this is a model that we want to expand to other places too. And of course, JPL has interns from all over the world. So from any universities in the US. So if somebody wants to have some really fun and do something very serious, good work, and are willing to put the effort into it, internships at JPL are pretty amazing. And then probably maybe some of the people listening would know that. So that's where we are. And the link is the same. And I just saw here a question. Let me see, what was that?
Well, I just wanted to post a link to the coverage for the, in terms of upcoming events, the Mars rover landing next Thursday.
Oh, fantastic.
So I recommend everyone to tune into that. That would be very exciting for us all. No doubt everyone at JPL will be, we'll have our 7 minutes of I don't want to say terror, but strong anticipation.
Well, hey, Tom, it's cold terror, so it's
well, let's hope the heat shield, stays intact.
Yeah, no, it's but it's just like, there is a time where we have no communication and we don't know. Let's see, what's this? Eventbrite, Colorado. Oh, Cynthia. Okay. Oh, so Michael Queen was, fantastic. Thank you for sharing that, Cynthia. Appreciate that.
No, Mike, I was just saying that you were from El Rancho.
Yeah. But so thank you so much for joining. Today we were, I think, 28 people at the max here, and we hope you enjoyed it. And I like to open all microphones to give Tom a big hand. And again, just make sure that you sign up next time. We're going to send out an invite, and feel free to forward that invite to anybody that you think should be part of this. But for now, let us open up all the microphones and give Tom a big hand. So I'm starting.
Thanks, everyone.
It worked, so what can you do with it? Anyway, yeah. So thank you so much, and Patel, good to see you again. And I hope I can say that to more people who are joining us today, that good to see you again. So till next time, have a fantastic time, and looking forward to seeing you next time. All right, see you. Bye-bye.
Bye, everyone.
Okay. Okay. Tom, we will have a list of people who not signed up, because that you don't really see the emails, but we have a list of people who are registered, and that will come from Francis. So
nice deal, Knut. Nice job.
yeah, it worked out pretty well, didn't it? And
Yeah, fantastic. I'll send you an email with stuff later, okay?
Yeah, fantastic, and include also Tom and Homa Jung on it, of course. But you always done that, so appreciate that.
Okay.
Yeah, and
have a good night. Don't forget to turn off the recording. All right.
No,
Take it easy.
Yeah,
all right.
I'm doing that right now.
Okay.
Stop recording.